Okay, welcome back to class, everybody. It's a pretty good time to get started. So let's just briefly review what we talked about last time. So we spent the beginning of class talking about the exam and going over an example solution to the exam. Then we spent some time talking about the projects and the deliverables that every group will have to do for the project. So I haven't yet scheduled the project order, but I'm going to do that very soon, maybe later this week or at the beginning of next week. And I'll email it out to everybody. So that way, if your group is one of the first groups that's going, you'll know well ahead of time so that you can put some significant effort into your presentation. We spent the remaining part of class primarily finishing Pyomo's shortest path. So we implemented a linear program for shortest path in Pyomo, and we were able to run it and solve it and get the shortest path out. And we just briefly started discussing facility location, and we didn't at all discuss homework 5, and that was because we postponed homework 4's due date to be not today but Thursday. And so the plan for today is to begin with your questions on homework 4. So I want to make sure that all of you are able to complete it on time, and if you have any questions, we'll take care of them today. And then after these questions, we'll talk about homework 5 and the key parts of that. And we'll go back to talking about Pyomo. In particular, when we did the shortest path example, I didn't spend very much time discussing how to switch solvers in Pyomo. So we'll see some examples of how to switch solvers and how Pyomo communicates with the solver, which might be useful for you in debugging and potentially trying your optimizations with various different kinds of solvers. And then we'll go back to facility location, which is another integer program that we're going to program in Pyomo. And we're likely not going to finish with that today, but if we do, we're going to continue to minimum spanning tree, which is going to give us a chance to do a dynamic optimization problem. So what I mean by that is it's going to be an integer program, but we're going to solve it many times, and as we're solving it, we're going to add more and more constraints to the program. So it's an example of an algorithm that's commonly referred to as row generation, and it's one of the very important things that you can do with Pyomo. So we're just going to do that as an example. But let's just begin with your questions on homework 4.
Can you do homework next week?
So right now it's due on Thursday. And so I want to, just ask, how many of you think you can finish it by Thursday? Okay, almost nobody. How many have finished it? Okay, next Tuesday. How many of you think can finish it by next Tuesday? Okay, it's going to be due next Tuesday then. Okay. But that's it. I'm not moving it back anymore after next Tuesday. Okay. So given that you guys are having some trouble with this homework assignment, I expect hundreds of questions from you on what the problem is and sort of what are the key things that are keeping you back from getting it done. Yeah.
I'm running out of memory. I think you addressed it earlier.
Okay, so are you running out of memory on the parallelization part? Or which part?
No, I got the parallelization part. But when I would try and run the gradient on the training set or top set, and the way it's vectorized it, I'm running out of memory.
So there's several reasons that you might run out of memory. So one reason that I ran out of memory as I was implementing it, so I had similar problems in my program as I was implementing it and making it better. So one of the reasons that I ran out of memory was because my stochastic gradient descent was holding too much history. So if you think about it, we're going to do 30,000 steps or whatever it is of stochastic gradient descent. And that's a lot of history of gradients and so forth to keep. And so one thing to make sure is that you're not, only keeping the right amount of that history. Another thing that might happen is when you're computing your gradients, so maybe you have some really nice vectorized code that doesn't have any for loops to compute the gradients. So that code might run out of memory because of replication of various arrays. So in there might be some issues. And so, yeah, those are the things that I would check.
But you should be able to do the gradient stuff.
Oh, yeah. I mean, obviously, I actually produce results out of my code, so my code doesn't run out of memory, and I'm not running it on some kind of special machine.
I thought the way you said in the homework, and I might have just misunderstood there, you might have talked about something else, was you had an if statement that if it indicated that you were going to run out of memory with vectorized code that you used before this.
Yeah, so my code tended to run out of memory when I use about more than 500 examples for computing the gradient, right? So we're going to pick this random subset of examples. So in my code, like when I have an if statement that looks, if it's less than 500 examples, then I use my vectorized code that has no for loop. And if it's more than 500 examples, then I use a for loop that minimizes some of the memory usage.
I guess you won't get the same answer if you just look at 500 samples at a time. So you don't want to break up the set into smaller samples because then you're not going to get the same W back.
That's right.
Okay.
That's right. So other questions? Yeah.
When I'm trying to calculate optimal W's, I'm getting negative values. Maybe something to do with the gradient.
So actually, we do want some negative values in the optimal W's, especially for a multinomial logistic. So let's sort of describe why we want some negative values in the W's. And the basic reason is that gradient picture. So let me just take a look at it here. So each step of stochastic gradient descent takes a step in the negative gradient direction of some distance, right? And this is what the gradient looks like if we do the first 30 example data points and we're looking at the fourth category, right? So the gradient has both positive values and negative values. And so if I take a step in the negative gradient direction, what's going to happen is all these pixels are going to have positive values associated with them, and all these pixels are going to have negative values associated with them, right? So let's think about what happens with those pixels in terms of the classifier, right? So this is the probability that the classifier assigns to the fourth class, right? So let's think of W4 here, okay? So the pixels that have positive W's are going to get multiplied by positive numbers here because the images are always positive pixel values, right? So positive W's are going to increase the probability of the class, and negative W's are going to decrease the probability of the class, right? And so if you look at this gradient picture, what's happening is that if I have a pixel value and any of these pixels that are going to have negative W's associated with them, that's going to decrease the likelihood that this is a 4. Right? So think about, for example, having a 9, right? So the 9 over here is going to be upping my likelihood that it's a 4, but down here it's going to be like severely degrading my likelihood that it's a 4. Does that make sense? Okay, other questions? Yeah.
My question is about the parallelization.
Yeah.
Specifically, I guess I'm a little unclear about the engine object setup function.
Yeah.
First, about how to create the loss function object, and then also how to then actually interact with loss function objects from the other, like from SGRED or something.
Okay, so the question is how to, basically like what should be roughly going on in these functions. Is that right?
Yeah.
Okay, so you can think of it like this. I'm going to have 4 engines. So let me maybe draw some pictures that might be easier than me just talking. So here I'm going to have engine 1, engine 2, engine 3, and engine 4. Okay? So each of them can have inside of it a little multinomial logistic loss function, right? So multinomial logistic loss, multinomial logistic loss, multinomial logistic loss, multinomial logistic loss. So these actually have the exact same code. Like all four of these have the exact same code. The only thing that's different about them is what data that they're working on, right? So this one is going to be working on the first fourth of the data set, right? This is on the second fourth, the third fourth, and then the last fourth of the data set, right? So each of these have a little compute grad function, right? And so I could send a message to engine 1 that says, use this object to compute the gradient using 20 samples, right? And I could send a message to this one that says, use this object to compute the gradient using 70 samples, and so forth, right? So those are the kinds of messages that are going to get sent to these objects, is sort of compute gradient with 20 samples. Here maybe with 70, here maybe with 10, and here maybe with 100. But what we've done is made sure that these numbers sum up to 200 samples, or how many ever total samples we want. And we split it so that it's one of those random sums that add up to exactly the number that we want, right? So we talked about that in lecture a few time periods ago about how to do that. Okay, so each of these objects is going to compute the gradient, but it's not going to do any averaging or whatnot. It's just going to return those sums, right? What's out here is one of these parallel loss objects. Okay, and it has a compute sgrad that got called with 200, right? So this parallel loss got called with compute the parallel loss using 200 samples. In here, it split those samples amongst these four engines. Each of them computed its own little gradient, and then returned it to this sgrad. So the idea here is split compute 4 or how many ever sgrads. And then how am I going to put those all together to return the sgrads from all the 200 samples?
You do like element by element addition?
Yeah, that's right. That's right. So I have these 4 answers. Each of them has a length 7,000 whatever coordinates. I'm just going to add those and then return the sum of them. So that's kind of the basic idea of the parallelization. So going back to your question, your first question was, what do I do to set up the engine data? Okay. What you do in that function is make sure that each engine creates this object, okay, and has the right set of data associated with the object. So engine 1 is going to have a different data set versus engine 2 versus engine 3. And you're going to do that because each engine has different parameters getting passed into it. And we did a tiny little example of that in class.
Yeah. And that can all be done with a single line, right?
That's right.
Yeah.
That's right. That's going to be like an apply that passes in different arguments to the various engines. Okay? So that's what happens here, is we just set up these objects. And then inside of the parallel loss sgrad, what's going to happen is the splitting requests to all the engines that go out in parallel, and then putting the requests back together with a sum after you get the answers back. Does that make sense? So this is an asynchronous request, to be precise. Right? So what's the difference between asynchronous and synchronous? So yeah, if I do synchronous, I have to wait for the answer, right? So imagine I do the splitting. If I did a synchronous request, what would happen is I'd send this request, wait for the answer. Send this request, wait for the answer. But then I'm not actually getting any speed up. So what's happening is I'm going to split, send out all the requests, and then have a bunch of requests that then here I'm going to do like request.get, which is going to force me to actually wait for the answer after I send it out. Does that make sense? So let's go back to the description. So I think that roughly should help you. So this sort of sets up the loss objects. And over here, there's something that might help you, right? So the reason that I have this function is because parallel loss needs to do several things. It has sgrad, it has sfeval, and it has feval, right? So for each of these three functions, it's going to need to essentially do the same thing, where it sort of splits out the calls, sends it to all the engines, and then puts it back together, right? So to split out the calls and send it to all the engines, we have to do one of those applies on a direct view that we talked about in class some time ago. So I don't know if you guys remember, but apply was the main way that we can send out a request to an engine. Okay, so but when I send out the requests here, I'm going to want to request the multinomial logistic sgrad, right? Here I'm going to want the multinomial logistic sfeval. Here I'm going to want the multinomial logistic feval, right? So these are almost the same calls. The only difference is which function of the multinomial logistic I'm calling, right? And the way to do that, and the way that I did that in my code, is by passing in the function name here, right? So it's apply loss function. So it means call some function on the multinomial logistic objects. And if I pass in sgrad as a string here, it's going to call sgrad. If I pass in sfeval, it's going to call sfeval. And if I pass in feval, then it's going to call feval. And with these arguments and keyword arguments. Does that make sense?
That does make sense. And then, and if I've done, or if we do the engine data store module the correct way, like once you set it up in that top function, you should just be able to use an apply statement and interact with interact. Like you shouldn't have to re-import it or anything.
So you might have to re-import it to be able to reference it, but it'll be there, right? So like the data is going to be there because you called this function first, and it set up all the data for these various loss functions, and here you can just refer to them. But in my code, I have an import statement here for engine data store and an import statement here for engine data store, but it's not because it's re-importing it. It's just because I want to be able to refer to those objects. Yeah.
And in general, the apply statement was most useful for calling.
Yeah, that's right. So that's what allowed me to make these calls to the various engines. So it's going to be apply some function on all the engines, and in particular, the function that I'm applying is this one.
I was just using this definition of that from the top of page 5 as sort of a check that I was doing the indexing and stuff, right?
Top of page 5.
Right. So below that function right there.
Okay. Yep.
So before you do the products there, those numbers, if I pass in a random set of W's that I generate,
yep,
they should all come out at about somewhere around a 10, I guess. If the argument of that product is probabilities that apply to these 10 digits, right? Exactly.
So certainly each category is going to have a number between 0 and 1, and they're all going to sum up to 1.
Okay, they're all going to sum up to 1. Okay, cool. So, well, and I guess the sanity check, as far as I was concerned, was if I'm just passing in random numbers and it's the first guess, they're all going to be kind of around 1/10.
Potentially, yeah. I mean, that seems not unreasonable, right? Because there's like symmetry in the way that you're generating your random number. So, yeah, seems not unreasonable.
Okay.
Okay.
Cool. So, well, and I guess the sanity check, as far as I was concerned, was if I'm just passing in random numbers and it's the first guess, they're all going to be kind of around 1/10.
Potentially, yeah. I mean, that seems not unreasonable. Right. Other questions about homework 4? Okay, so how about just some discussion? Let me ask you some questions, which is, can you describe just what are some of your major difficulties in implementing the homework assignment? Like, what's the hardest part? Or what are some of the hardest parts?
Right now, I'm just stuck on the first basic concept of like how you apply stochastic gradient descent to different types of problems last time. Like we talked about with a bunch of different people, and I think I have the idea. But
Okay, so the main question is, it sounds like it's just a conceptual jump from optimizing parabolas to optimizing now these more complicated looking classifiers. Yeah. Is that right? Okay, so great that you talked about it with other people. So that's the number one thing I'd encourage everybody to do with basically any of the problems that you're having. And usually what happens is you have like 2 or 3 friends and you tend to sort of talk to the same people. But there's a lot of people in class here that have like lots of different views on the problem. So I encourage you to sort of like just talk to some random people in class. Like, it might help. But my sort of comment on that is you can just think of this as a function, right? You can think of stochastic gradient descent is dumb. Like, it knows absolutely nothing about what this function is, whether it's a parabola or what it is or why we're doing it, right? It just does minimization. And so this just happens to be the function we want to minimize this time instead of the parabola. But the interpretation of that function is this maximum likelihood, that we're trying to find the W's that give us the maximum likelihood of the data set. Okay, other comments in terms of what's most difficult or what was most difficult for you in this assignment?
I mean, I think the indexing
Absolutely.
is very difficult. I originally, still, I guess, I noticed that when you pass in like an array of an initial guess of x, in the example you do like 2 by 7,840.
Yeah.
I initially wrote mine as like a 3-dimensional thing.
Yeah.
So like 2 by 10 by 784.
Yeah.
That's, that cost me, I think, a lot of time, because then when I just ran into, it just was a pain.
I absolutely agree that vectorizing this code is significantly more difficult than what we did in the previous assignment. And it's something that I spent a lot of time debugging when I was programming this. And the only thing that helped is doing it very slowly, right? So, and in fact, when I implemented it, I think I first implemented it so that it works with a single sort of W, and then switched that code, like vectorize it as much as possible for a single W, and then switch that code to work for multiple W's. But certainly it was one of the things that was conceptually most difficult, and it definitely involved some pencil and paper and writing down the dimensions of various arrays to make sure that the broadcasting is working correctly. It was not something that I could do just off the top of my head without writing down the dimensions of things. So, yeah.
What did you, not, that whole argument for 1 to 30 or 1 to 50,000, that isn't what should sum up to 1, but for each digit I.
Yeah. Yeah. That's right.
Okay.
That's right. Okay, any more comments or discussions on assignment 4? So just to kind of step back from this particular assignment, this kind of problem is incredibly useful, right? So companies use this all the time. So classification is one of the key optimization problems that lots and lots of companies do. And stochastic gradient descent is the way to solve large-scale problems like this. And so from that perspective, you guys are learning basically the core of how most machine learning tends to work today. But yeah, there was another question.
I have one confusion with cascading is that
Could you say again?
confusion
Okay.
So is the randomness in selecting the n data points, or after selecting n data points, we again have to make one more, write some more lines of code where we...
No, it's the randomness is in selecting the data points. So if I say 300 and we're working with the full set of 50,000, then it's like which 300 out of the 50,000 we're going to select.
So it's not like in the parabola case where we choose one.
Right. In the parabola case, our randomness came from picking a random direction and so forth. But here, the only randomness is coming out of selecting a subset of the 50,000 to compute S-grad.
Is the expectation that we equal to the gradient of...
Say again?
But we have to make sure that the expectation of the n data points that we have to choose should be equal to the...
That's right. That's right. And so the way to do that, or the way to think about that, is that you are going to return the average of the points, right? So imagine returning the average of 50,000 versus picking 500 randomly and returning the average of those 500.
And that's why we are dividing by n data.
That's right. That's right. And that's why, yeah, exactly. That's why a lot of these functions here have a parameter that says, like, do I want to divide by the number of data points? So it's not these functions, it's the ones up here. Right, so do I want to average? So true in some cases. But when I'm calling them in parallel, I don't want to average. Right, because I want just the raw sums, because I'm then going to sum them and average overall at the end, right? So when we're calling these in parallel, the average is going to be false. But when we're doing it for a single loss, the average is going to be true. Make sense? Yeah.
You have average option for every sub-function, but why don't you have it in graph?
Oh, because grad computes it on all of the gradients.
Because you have graph up there, and you have.
Yeah, so potentially you could add an average option here, and it's probably because I didn't use this function. Probably I always use sgrad everywhere, but that's a good observation. The code would probably be better and more symmetric in terms of this if I had an average option here as well. Okay, any more questions on homework 4? Okay, keep working hard on it. Let me know how it's going on Thursday. But I do think that all of you can finish it by next Tuesday. Okay, so let me know how it's going. So given that we're going to postpone homework 5 until next Tuesday, I'm just going to skip the second part of today's plan, which was introduce homework 5. We're going to do that on Tuesday, or maybe on Thursday. And the plan for today is to just talk some more about Pyomo, and in particular switching solvers in Pyomo, and then facility location. So let's go back to our Pyomo example and quickly recall where we were and what we were doing. So this was the example code that we had. So I'm not going to write out the linear program again, but if you recall, we had some y's that were our variables. Our objective was the sum of the y's times the arc lengths. And then we had a bunch of constraints that were equality constraints that look like sum up everything that's going into a particular node, subtract everything that's going out of a particular node, and that has to equal the node imbalance. So that's what we programmed in Pyomo. And then right here is where we call the solver with Pyomo to actually get the results. So in particular, what we have right now is I'm calling Cplex with the solver, and that happened right here when I did solver factory and I passed in the string Cplex to that. So what Pyomo does here is it searches the path, the executable path on my machine. And in particular, it's looking for the Cplex executable, so which happens to be installed right there. And that's the executable that Pyomo is going to call to actually solve this problem. Okay. So let's take a look at the actual solve call, and in particular, the parameters that I'm passing in there. So I'm telling the solver to solve the model that I created, so that's the Pyomo object model. But let's take a look at the rest of these parameters here. So the first says t equals true. So that what that does is it actually prints the solver output to the screen. So I may or may not want to do that, but for debugging it's incredibly useful to see what kind of bugs or what kind of reports Cplex is printing out to the screen. So that's what that is doing. So here I'm saying keep files equals true. So Pyomo communicates with the solver by writing out a bunch of files to disk. And we're going to take a look at these in just a moment. And again, this is a useful debugging tool. It's to see how Pyomo is communicating with the solver, because there might be a bug in there somewhere. And the last is some option strings. So options are basically tell the solver which algorithm to use or what kind of tuning it should do on the algorithm to actually solve your problem. And in particular, what we're solving here, what we might be solving is a mixed integer linear program. And two key parameters for that is what should be the optimality gap between your best lower bound and your best feasible integer solution. So here I've set that to 0. And the second one is, as you're solving this problem, you keep solving LP relaxations of it, where you change the integrality constraints to things like bigger than or equal to 0 and less than or equal to 1. So how close does a number have to be to 0 or 1 for you to consider it actually integer? Okay, so that's what the integrality tolerance here is. So I've made that relatively small. So these are slightly tighter parameters than the default parameters of Cplex, just to make sure that when I solve it, I actually get out the optimal integer solution as opposed to something that's just near optimal. Okay, so let's run this and let's take a look at some of the output. So let's take a look at the first few lines, and these few lines come out of the fact that I passed in keep files equals true. So Pyomo here is printing out all the files that it used to communicate with the solver. So this is the solver script file. So let's take a look at it. So this is what Pyomo actually executes to call Cplex. Okay, so it calls Cplex and then sets Cplex's log file to be some temporary file name it generated. It sets the two options, that Cplex options that I had passed in with the option string. Then it reads in the LP, so that's the way that it actually communicates the linear program it created to Cplex. Then it displays some problem statistics, optimizes, and writes out the solution, and then quits. Okay. So let's take a look at some of the rest of the files. So an interesting one is this LP file. So this is what Pyomo is actually passing to Cplex to describe the integer or linear program that you want to solve. Okay. So minimize this objective, so these are the various variables and their coefficients, such that, and then these are the various constraints. So as you can see, this is all just computer-generated names, right? So not particularly nice to read for a person, but it might be useful for debugging, just in case you want to make sure that Cplex actually is getting the problem that you're intending it to be getting. And you can also see the benefits of writing things in Pyomo versus writing it sort of directly to Cplex. So if we were writing it directly to Cplex, we might have to use syntax that's more like this. Okay, so some other interesting things, the log file. So the log file is going to basically contain the same thing that gets printed to the screen. So which is all these things about Cplex starting, setting the various integrality tolerances, and then these printouts that tell you things about how many variables, how many constraints your problem has, and then information about your actual solution. But let's take a look at how then Cplex communicates the solution back into Pyomo, which is through a file like this. which again is just not particularly nice for a human to read, and not particularly nice for your programs to work with. It's just an XML file, but it might be useful for debugging, right? So you can see that Cplex thought that the solution status was optimal, that it had various infeasibility and so forth criteria, and then, here's the objective function value. So again, just various ways that you can double check that the communication is happening correctly. And this is the values of the various variables that Cplex is passing into Pyomo, and then Pyomo automatically reads back into Python so that you can use in your program. Okay. Okay, so let's say that for whatever reason I'm unhappy with Cplex and I want to switch to a different solver. So, yeah.
Last time you did show us how to print out the entire module within the program. Is it possible to print it to a file?
Oh yeah, I think so. So let's see. So this is the way that I printed the model just to the screen with the pprint function, and that may itself have an option. Yeah, so you can pass in a file name, and it'll probably write it to a file right there. Okay, so going back to here, suppose that I'm unhappy with Cplex for whatever reason. It's not solving my problem correctly. There's various other solvers that you can use. So some of those are free and some of them are not free. So Cplex has a free academic license. And if you haven't installed it or haven't looked into installing it on your machine, you might take a look at doing that. But the nice thing about Cplex is it's a commercial product. So it's highly optimized. It regularly solves enormous optimization problems, and so it's not likely that there's a bug in it, okay? Because many people use it. There's another similarly well-known commercial solver called Gurobi that also is highly unlikely to have a bug in it and regularly solves enormous problems. So one of the main things that changes when you change from one solver to another is these options, okay? So Gurobi has the same kinds of options, but they're going to be called something different. And I don't know off the top of my head what they're called in Gurobi, so I'm just going to remove this option string, okay? But you could go and read the Gurobi documentation and find out what the corresponding parameters are and then pass it in as options into that as well. So let's delete this and then try to resolve things. Okay, so again I'm getting out the various Pyomo debug things that tell me the various files that Pyomo is using to communicate with the solver. But you can see now that the actual solver output is different, right? So we're not using Cplex. We don't get the Cplex output anymore. We're getting Gurobi's output here. But again, similar kinds of things that output the objective function value and so forth. And maybe we can just take a look at, let's take a look at the solution file to see if that's any different. Okay, so as you can see, Gurobi's method of writing out the solutions is very different than Cplex's method of writing out the solutions. So in Cplex there was that XML, but in Gurobi there's this kind of YAML, I think, file. And so Pyomo sort of done a lot of the work for us to make sure that it translates correctly between all the various ways that the different solvers take in their input and their output, so that your program looks exactly the same regardless of which one you're using. And let's try one last solver, which is just a freely available open source solver, GLPK. And so we get very similar kinds of outputs. So the log file, the solution file, the problem files, and then now we're getting the GLPK's output from solving a linear program or a mixed integer program, which again looks very, very different than both Gurobi's and Cplex's. And let's maybe take a look at how GLPK outputs its solutions, which my guess is in yet a third format. Yeah, so yet a third format of outputting the solutions. And so I hope that you can see the enormous advantage that using Pyomo brings as compared to using any of these solvers directly, right? I didn't have to change my code almost at all to go from one solver to the other, even though fundamentally each of them is a significantly different piece of software, right? They take different options, they describe the problems in different ways, and so forth. Okay, so great. We're going to become more familiar with Pyomo, and in the next homework assignment, in homework 5, you're going to be writing some linear programs in Pyomo to solve reasonably large problems. But the next example that I want to do in terms of Pyomo is facility location. And let's just remind ourselves, we had just a brief discussion of facility location towards the end of class last time. So the idea was something like this. So we have a graph where we have a bunch of nodes, and each node has one customer on it. And we have a bunch of arcs, and each arc has a length associated with it. And we're a large company like Walmart, and we want to figure out where to place our Walmart stores or our warehouses so that they're easily accessible by the customers. Okay. So the idea was that we want two things. We want to minimize the distance that a customer has to travel to their nearest store, and we also there's also some opening costs. So it costs me some amount of money to build a store in this location that might be different to the cost that it cost me to build a store in some other location. And so that just described the problem in English, but where we had ended was that we wanted to create an integer program to help us solve this problem for a general network. And I had an example here of a bunch of nodes, and there's various opening costs for these nodes. And we just started trying to describe what the problem is. So in particular, we had decided that the important sets in this problem were the nodes and the arcs, and we had just started describing some variables. So the variables are what I want to decide, and the decisions here are, do I open a store at location I? So we decided those are yi's. And does customer at location j go to a store at location I? So those were xji's. So does the customer at location j go to a store at location I? So given these variables, can you help me write down an objective function? Okay. So remember, the objective function had two parts. So one was the total cost for me to open all of the stores that I'm going to open. And the second part was the distances that the customers have to travel from their location to the nearest store. So, and I'm going to want to minimize those things, right? So that part is easy because I want the lowest cost possible. So help me write down the total opening cost for opening all the stores. So say again? Great. Right, so this is some data that's the opening cost. Okay, so help me write down the second part of the objective, which is how far customers are going to travel to their nearest store. So this part's a little bit more difficult, but not too much more. Yep. Yep. That's right. So this is going to be the distance, so let's call these JIs and XJI. So distance a customer at J has to travel to get to I, right? Yeah.
We should also probably multiply with some factor to, because both are different dimensions. So
Yeah, so that's a great point. So the point is he's worried about units. He wants to make sure that these are the same units. And in general, that's true. That there could be some factor here that sort of trades off between the two. But let's skip that for now. But that's a very important thing in terms of solving a real-world problem, is understanding how these two things are trading off against each other. But for the purposes of right now, let's just skip it or assume that it's 1. Okay? So I think this is a great start. So we have an objective. There's a slight problem which we're going to solve later, which is that these distances don't directly come from the graph, right? So if you look at the graph, all I had there was a bunch of edges with lengths, right? But if I ask you how long does a customer at 5 have to travel to get to a location at 2, like I can't read it directly off of the edges. I have to actually solve some shortest path problem that's going to tell me how this guy walks from 2 to 5. So we're going to take care of that later. But help me figure out some constraints here. So what are some reasonable constraints that's going to describe the rest of this problem? Yeah, so every customer has to go somewhere, right? So how do I write that? So customers are J's. So for all customers, the sum of right? So if I take a look at a particular customer, the JS customer, and I take a look at all of the locations, that customer has to go to exactly one of them, right? Okay, great. What are some other constraints I might have? Yeah, that's right. I might have some number, like I want to open up 2 stores, something like that, right? So how do I express that? So that's my limit on the number of stores. How about some other constraints? So this is not quite enough. Yeah, that's right. Because right now, what might happen? So right now, I might make the x's so that the customer is sort of walking to a place where there is no store, right? So how do I say that customers can only go to places where I've actually put a store? Yeah, so it is going to connect the x's and the y's, but how? Yeah. Right? So it says that this customer, so the JS customer cannot be served at the IS location unless the IS location is open, right? So if the Y is 0, then no customer can go to that location. So this looks not unreasonable to me. Perhaps we have some bugs in it, but let's go and actually try to implement it with some data to see how we can translate this integer program into actual code that we can solve with Pyomo. Okay, so just to remind you, I had 2 data files. So one was distances. So that describes my graph. So these are all my various locations, and those were the distances between every pair of them, right? And then I had some open costs, which described the cost of opening a store at the various locations, okay? Okay, so I'm going to start us off here with distance data frame is pandas distances.csv, and then I have my open cost data frame is going to be this open costs.csv. Okay. So the first thing I want to do is I want to make sure that before I start creating the Pyomo model, I actually have all the things that are required for it, right? And the things I need are the sets and the data that are going to go into making the model, right? So the sets are relatively easy. So how am I going to get the set of locations and the set of customers? Where am I going to get those from? So where's the set of locations and the set of customers in these CSV files? Yeah, I can just, for example, I could take a look at these locations, right? And if I assume that every location shows up here, and there's one customer in every location, this is my set of locations and my set of customers, right? Another thing I could do, sort of depending on the way that I define my inputs, is maybe just take a set of these, right? Because maybe something appears here that doesn't appear here. In which case, you know, maybe that's my set of customers and this is my set of facility opening locations, because they might be different, okay? So let's maybe do it that way, that we're going to define our set of customers by looking at the graph, and we're going to define our set of facilities by looking at the opening cost CSV file, okay? So let's just write some code here. So facility set is equal to open cost data frame dot location dot unique, right? So that should give me all the unique locations from that. And then the my customer set is going to be my distance data frame dot start node dot unique plus my distance data frame dot and destination node dot unique. Right, so that should pull out all the customers and all the and let's run it to make sure that we're doing things correctly. Okay, so unsupported plus for set and set. So say again? I think it's dot union. Let's see if this works. And now if I look at my facility set, it's 1 through 5, and if I look at my customer set, it's 1 through 5. So one happens to be an array and the other happens to be a set, but it's okay for now. We can switch it, you know, we can even switch it to an array right away. So we can make this a list if we wanted to. Okay, so I have my set of customers and I have my set of facilities. But the next bit I need to make sure is that I can access the opening cost and I can access these distances so that I can write the objective function in my Pyomo model, right? So accessing the opening cost should be really easy because they're right in that pandas data frame, the open cost data frame. But here I have to do a little bit of work. In particular, it's because these distances don't directly come from the data frame. I have to actually do some network manipulation for that. Any suggestions on how we might get those distances? Yeah, and where would I find that? Oh yeah, so I could use the LP. There's a nicer way to do it though. So what other way can we find shortest path that doesn't require me to use Pyomo? Yeah. Yeah, so Networkx has a bunch of networks algorithms in it, okay? So let's take a look at Networkx and what it can help us with. Okay, so Networkx has this entire subpackage called algorithms, where it's implemented a ton of different algorithms. And I sort of know what I'm looking for here, but if you didn't, you would spend some time reading the documentation. And one of the things that you could find is all pairs Dijkstra path length. Okay, so let's read what that does. Okay, so compute the shortest path lengths between all nodes in a weighted graph. So the weight is, again, how we're going to store the edge lengths in Networkx, and then returns a distance dictionary, so a dictionary keyed by source and target of the shortest path lengths. So let's try to do this, because what it's going to do, it's going to compute the dij's for every I and for every j, right? Like all pairs in the graph. But to do that, I have to actually convert my distance data frame into a Networkx graph, right? So help me write some code here to convert the distance data frame into a Networkx graph. So what's the first thing I want to do? So does what I'm doing make sense, or do you guys have questions about that? So this data frame is just a bunch of rows, and each row has an edge on it, basically, right? And I need to turn that into an actual graph object so I can call this algorithm on it. So the first thing I need to do is maybe make an empty graph, right? So and I'm going to make a undirected graph, because here, like, I'm not making a distinction if we're walking from I to j or j to I. It's going to be the same distance either way. Okay, so then how do I actually make the graph? What do I do? Yeah, that's right, but I need to probably do a for loop or something like that. So for, let's see, row in distance data frame dot iter rows g dot add edge, and I don't remember, let's see, the distance data frame has what columns in it? Start node, destination node, and distance. So I want to do row start node, so I want to add an edge from the start node to row end node, or was it called destination node? Yeah, dest node. And then I want to associate some piece of data with that, and let me call it length, or maybe we call it distance. Let's call it distance, why not? So distance is row dis. So let's see if this runs correctly. Okay, so tuple indices must be integers and not strings. So I may have forgotten exactly what iter rows does. Okay, that's right, because I need the index and then the data, right? And this is probably data and data and data. So the bug there was that iter rows returns two things: the index of the row and the data associated with the row. So let's do it again. And now if I look at g.edges with data equals true, it looks, pretty reasonable in terms of what it should look like. So now let's call, let's say that answer is going to be networkx.algorithms all pairs Dijkstra path lengths So all pairs Dijkstra path length, and then passing in the network G. So let's take a look at what answer looks like now. So it's basically telling me that the distance from N1 to N1 is 0. The distance from N1 to N2 is 1. The distance from N1 to N3 is 1, and so forth. So that's not quite what I expected, right? So, because the distances I have should be tens. And so where's my bug? It's the fact that here I have to pass in a weight, right? So I need to pass in something like weight equals dist. So let's try to rerun everything and see if we're okay. So now it's looking more reasonable, right? So some distances, so N1 is 0 away from N1 and 10 away from everything else. Some distances between N2 and N5. So it says that N2 to N5 is 20, and maybe let's quickly go back to our picture to make sure that that's true. So N2 to N5 is 20. Yep, that makes sense, right? Okay, so this looks pretty good. So now help me write the Pyomo code, because I should have everything that I need, right? So I have the sets that I need, I have the data that I need. So now I just need to write all the code to stick everything into the integer program that's actually going to solve the facility location, right? So how do I start? So here I just imported the Pyomo environment SPE. So the first thing we want to do is create a concrete model object. So it doesn't have any sets or variables or constraints with it yet. Yeah.
So here in the answer we just have that like we haven't ensured that so if from node A to B there is some path, it might involve two edges. But we just have taken a distance from A to B as the distance we got from the shortest path. Yeah. But our constraint that we have is we make sure that customers go through certain edges, and then the flow should be less than yi, right? Right. So but that's different. So that it just says that a customer can't go to a location where we haven't built a facility. Yeah, but the customer. In the shortest path, when we calculate the shortest path, we know that the customer is going through some edge, right? Yeah. But we are not making when we are selecting that particular distance, we are not making sure that the customer is going through that location, right? So if the customer needs to get to some place, he's going to take the shortest path to get there. And it doesn't matter whether in between like their facilities or what's going on in between, because all he's going to do is just walk from his location to the place of the nearest facility. Another question back there? Okay, so here I just want to start with concrete model. Okay, so I created the concrete model. So what's the first thing that I need to do after I create the model object? Yeah. Yep, create the sets. So here I'm going to have a facility set, and that's going to be a set, and I'm going to initialize it with my facility set, right? Which I had computed previously. The next thing I need to do is my customer set, which I'm going to initialize with my customer set. And I like to just check things as I'm typing them. So let's see that we did this correctly. So if I do m.facilityset.pprint, so it's a facility set, it has those members in it. And if I do the customer set, it's a customer set and it has those members in it. Okay, so that's making sense.
So what's the next part that I need to do after I've created the model object and I've created the sets? Yeah, I need to create some variables, right? So we had two different kinds of variables here, right? So we had y's and we had x's. So so how many y variables did we have? Yeah, so one for each facility. So the way that we say that is by saying there's a variable for each facility in the facility set. Does that make sense? So here I'm basically telling Pyomo, do a loop creating a variable for each member in the facility set. Now, what's the domain of those variables? Yep. So they're 0, 1. So we're going to do p.binary. Okay, so we also had x variables. And how many x variables do we have? Each pair of customer and facility. So right, so that's a cross product. So I need to say somehow the cross product of the customer set and the facility set. So Pyomo has some really nice ways to describe set cross products and so forth. And the way to do that is by saying customer set times m.facility set. So now we're going to get a variable, an x variable. For each customer is going to be the first index, and then a facility is going to be the second index. And those variables are binary as well. Okay, so let's run things and see that things are working out to plan. And in particular, let's take a look at the x's. Okay, and this makes sense, right? So it's basically saying, is the customer at N1 going to the facility at N1? And the lower bound is 0, and the upper bound is 1, and its current value is none. And the domain is binary, right? So it's looking correct. And if I do m.y.pprint, similar thing. I get 5 of those, 1 for each facility, and their domains are binary.
You have something for set minus, for example, say if we don't want to open facility at certain locations, then we might have to do a...
So one way that you could do it is you can actually set these variables to 0. You can force Pyomo to say, like, it's kind of like adding a constraint equal to 0, but you can actually say that the variable yn2 is equal to 0.
But I want the node to be there, but not a facility to be there.
Yeah, so that's exactly what's going to happen. If I set the y equal to 0, I'm forcing a facility to not be installed. But there's other ways to do it as well, but that's one way. Okay, so what's the next part? So I created some sets, I created some variables. What should I do next to describe my integer program? Yeah. And how do I define an objective in Pyomo? What's the first thing I need to do? Yeah, create a rule function that's going to create the expression for the objective, right? So, and what does that rule function take in? It just takes in a model, right? A model object. Okay, so what should this return? So you're doing the first part of the objective, which is the y's times the opening costs, right? So m.y sub I times. Okay, so now we want to be a little bit careful. So our opening costs are in this opening cost data frame, right? So I need a way to say, give me the open cost for this facility. So how did we do it before? When we did shortest path? Yeah, we changed the index of the data frame. So let's do the same thing here. And I don't think that we used the open. Okay, so we used it here. But let's right there. which is change the index of OpenCDF. So OpenCDF dot set index, and I don't quite remember exactly how this works, but here we would pass in location, right? So let's see if this does things correctly. Oh, and my problem was that I had some invalid Python syntax here, but okay, so now, now my index is the actual location, and then that's going to correspond to costs. So here I want the sum of the y's times OpenCDF at that index dot cost, right? And then for I in m dot facility set, right? So hopefully that should do the right thing. So let's run things and debug before we add more to it. So how do I debug? I can call this objective rule function and pass in my model object and see what happens. Okay, so I got a key error, so let's debug and see where that is. So I is n1, and I think it's because I need .ix, and then maybe like that. Let's see if that works better. Okay, so this looks, not unreasonable, right? So I'm getting my y's times the various opening costs. So the opening cost for N1 was 50, the opening cost for N2 was 1,000, and so forth, okay? So it looks like the first part of the objective function looks pretty reasonable, right? Okay, so help me write the second part of the objective function. So now, again, I'm going to be summing over some things. So what's the... Say again? Yeah, m.x. And then there's going to be two indices, right? The customer j and the facility I. And I have to multiply that by the distances between them, right? And I can get those from looking at answer j and answer I, right? And now I have to iterate over all combinations of customers and facilities. So the way that I'm going to do that is for j in m dot customer set and for I in m dot facility set. Okay, so this may be new syntax to you that you haven't seen before, but I think it's sort of straightforward to explain. So when I have two for loops here, it's like a nested for loop, right? So let's run this and see if it works correctly or not.
Is he getting that answer ji from the nested for loop? Or did we already?
So yeah, where did we get? Yeah, answer ji comes from this, and I should have probably called it something different. Let's call it distances.
Okay. So you defined, your network was already defined, and now you're just making your...
Now I'm accessing the answer that I got from all pairs shortest path. Okay, and just looking at the objective, these are all the y's that were at the front, And then these were the various distances. So for example, the distance from N2 to N5 was 20. And so I got 20 times the x from N2 to N5. Okay. So it looks like we're making progress. So just a couple of comments. We're going to finish this next time. But one big comment that I have is the code that I've written right now is reasonable, like it makes progress, but it's actually like really not nice, right? Like it's kind of hard to read, it's hard to reuse. And so often what I do is I'll spend some time writing it like this, but then I'll rewrite it so that it's in a nice class format, the same way that shortest path code was. Because then I'll just have a single class, and if I want to solve facility location again, I just use that class instead of having to think about all the different subparts of everything. Okay, thanks a lot for listening, and I'll see you all next time.